Hello everyone and welcome back to the series of digital logic design, and today we will study about the encoders. Earlier we have studied about the decoders, which is used to implement binary code on hardware, where encoder is a digital circuit that performs the inverse operation of a decoder. A decoder has 2 power n or less or equal to 2 power n input lines and an output line, as we were having an input line and 2 power n output lines in decoder, where in case of encoder, input and outputs are opposite. The output line as an aggregate generate the binary code corresponding to the input value. In the case of decoder, we have studied the example of binary to octal converter, and now we will study the opposite circuit, which will be octal to binary encoder. For this circuit, we will have octal input, and corresponding to the octal number, we will have binary code in output section. So the input variables will be from D0 to D7, and output variables are X, Y, and Z. Here it is also assumed that only one input have a value of 1 at any given time, while all other inputs are 0. And corresponding to this single input, a single output code is being generated. Now the encoder is implemented with OR gates whose inputs are determined directly from the truth table. Like the output variable Z is equal to 1 when the input octal digit is 1, 3, 5 or 7. Or we can say that whenever the octal input is odd, the binary variable Z will have a value of 1. Next, the output variable Y have a value of 1 for octal digits of 2, 3, 6 or 7, and the output variable X have a value of 1 for the octal digits of 4, 5, 6 and 7. These conditions can also be expressed by the following Boolean output function, such as Z will be equal to sum of D1, D3, D5, D7. The output variable Y will be sum of D2, D3, D6 and D7, where the output variable X will be equal to the sum of D4, D5, D6 and D7. So this decoder can be implemented with 3 OR gates, one for each output variable. The encoder defined in the truth table has the limitation that only one input can be active at any given time. For instance, if 2 inputs are active simultaneously, then the output produces an undefined combination. For example, if D3 and D6 are simultaneously 1, then the binary output code will be 1, 1, 1 because all the 3 bits are equal to 1. This is due to the fact that for D3 the output code is 0, 1, 1, and for D6 the output code is 1, 1, 0. So the combined output will be 1, 1, 1. This is due to the fact that input variables are directly summed in the output variables. Now the output code 1, 1, 1 represents D7 and it doesn't represent binary 3 or binary 6. Now to resolve this ambiguity, the encoder circuit must establish an input priority to ensure that only one input is encoded at one time. So if we establish a higher priority for inputs with higher subscript numbers, like if both D3 and D6 are active at the same time, then the output 110 corresponding to D6 must be generated because D6 has a higher priority than the D3. Now, the another ambiguity in the octal to binary encoder is that an output with all the zeros is generated when all the inputs are 0. But this output is the same as when D0 is equal to 1, which means that if no input is applied, then all the output bits are 0. And if D0 is active, which corresponds to 0 octal, then again all the output variables are equal to 0. This discrepancy can be resolved by providing one more output to indicate whether that at least one input is equal to 1. And if all the inputs are 0, this output must also be 0. So in normal encoders, we were having two issues which we have discussed. Now to overcome this, we will use a priority encoder. A priority encoder is an encoder circuit that includes priority function. Now the operation of the priority encoder is such that if two or more inputs are equal to 1 at the same time, then the input having highest priority will take the precedence, which will resolve our first problem. Now, if you look at the truth table of 4-input priority encoder, in addition to its two outputs X and Y, the circuit has a third output designated by V. This is a valid bit indicator that is set to 1 when one or more inputs are equal to 1. This will solve our second ambiguity. Now, the other two outputs are not inspected whenever the valid bit indicator bit is equal to 0 and are specified as don't care condition. Note that the X in the output column represents the don't care condition. The don't cares specified in the input columns are useful for representing a truth table in the condensed form. So instead of listing all the 16 minterms of 4 variable, the truth table uses don't care to represent either 1 or 0. For example, x100 in the third row of the truth table represents the two minterms, which are 0100 and 1100. And also note that in first row, whenever the output valid bit indicator is 0, then the output values of X and Y are not valid, so they are not considered. Now according to the table, for the priority encoder, higher the subscript number, higher the priority of the input, which means that input D3 has the highest priority. So regardless of the values of the other input, whenever the D3 input is 1, the output of XY must be 1, 1, which will represent a binary 3. Now D2 has the next priority level, so the output will be 1, 0 if D2 is equal to 1, provided that D3 is equal to 0 regardless of the value of other two lower priority input. Now the output for D1 is generated only if the higher priority inputs are 0, like D2 and D3 are 0, and so on down the priority levels, like D0 is equal to 1 and D1 is also equal to 1. So the output code of D1 will be generated. Now to make the output circuit for priority encoder, the maps for simplifying output X and Y are shown in the figure. Although the table has only 5 rows, with each X in a row is replaced first by a 0 and then by a 1, which is by definition of a don't care, that a don't care can be a 0 or can be a 1. Through this, we will obtain all the 16 possible input combination. For example, in the fourth row of the table with inputs XX10 represents the 4 minterm 0010, 0110, 1010 and finally 1110. The simplified Boolean expression for the priority encoder are obtained from the map. The condition for output valid bit indicator V is an OR function of all the input variables. The priority encoder is implemented in the given figure according to the following Boolean functions for X, Y, and V. Thanks for watching the video and stay connected for more interesting videos.